All right, we're going to pick up with example 4. We kind of talked about it yesterday as the bell was ringing, but example 4 kind of looks at it a little bit slower. The synthetic substitution / synthetic division process is just an algorithm that someone came up with to make evaluating and or finding remainders a little bit easier. But it basically, the substitution part generates out of what's called the nested form. And nested in this case doesn't mean that there's going to be birds living in it, right? Although that would be cute. Nested just means that it's something inside of something, and then something inside of something else, inside of something else. So like the Russian nesting dolls, right? They're not birds, but you have a doll inside of a doll inside of a doll, okay? So that's what nested means. And if you've done any programming, you've heard of nested loops probably, where you have a loop inside of a loop, a subloop. It is. Okay, so let's look at nested form a little bit more slowly. This is the same function as yesterday. You have a cubic polynomial. It has 4 terms. And the way you put something in a nested form is once it's written in standard form, which it is right now in descending order, you're going to group everything together that has an x. And I'll color code it. So in red we have 2x cubed plus x squared minus 13x. And then we have this plus 6 out there, plus 6. Now, what do? We then factor out an x from the ones that we've grouped together. That's the associative property of addition. And we're going to factor it out on the right-hand side, which, since multiplication is commutative, should still work. Okay, so I factored it out on the right-hand side. And then I still have my purple plus 6. Well, that was so much fun, I think I want to do it again. So I'll choose a different color here. And now I will group these together on that line. And I will factor out an x from there. So if I use the same color coding here, we got an open parenthesis. And then I got another open parenthesis. 2x plus 1 times x. And then I finish my red layer, minus 13, x. And then I got the purple layer, plus 6. And we can stop there because if you go inside the innermost parentheses, you just see 2x plus 1. Okay, so if you wanted to do something there, you could maybe change the color. Let's choose a different color here, like burnt orange. And you could put like a parenthesis around that x if you want, like that. So just because when we evaluate it, we want to be able to then go from left to right. You could factor it on the left, but factoring it on the right, as you'll see, allows us to move from left to right when we evaluate. So it's just a little bit easier in that respect. Now, it's the exact same function, but let's go ahead and evaluate g of 1. Okay? So if this is the same as g of x, let's evaluate right below there g of 1. So we got g of 1 on the left, and now let's kind of just do this together. I don't think we actually need to plug in. Okay, so I'll use my pointer here. Your dear Aunt Sally is in the house now, right? And the P in please excuse means parentheses. So if you're going to evaluate a 1, this is the one that has to be, well, actually, you know what? Let's actually physically just plug it in but not evaluate it. So 2 times 1 plus 1 times 1 minus 13 times 1 plus 6. Okay? We could do that at least. Now let's evaluate it. Let's simplify it in one step. Okay, so now if we're evaluating it, you come all the way here on the inside, and look what we're doing. We're first doing 2 times 1, so we're multiplying. That's what? 2, right? And then we add 1 to get 3. Now I have 3, and this is why we do it on the right-hand side. I can then multiply 3 by what? 1. I get 3 again, minus 13, which is negative 10. And then I multiply again, times 1 is negative 10 plus 6, negative 4. So g of 1 is equal to negative 4. And notice what we did there. All we did was multiply, subtract, or add. Multiply, subtract, or add. Multiply, subtract, or add. So really, subtraction can be defined in terms of addition. So it's really just multiply, add, multiply, add, multiply, add. And it's an aggregate number. We're changing it as we go. We're not having to memorize anything. Now, if we were to plug it into the original problem, let's verify that it's the same. That's called synthetic substitution or nested form substitution. If I use direct substitution, I get 1 to the third power, which is 1, times 2 is 2, plus 1 squared is 1, minus 13 times 1 is minus 13, plus 6. So notice I have to do this now as a two-step process. I have to evaluate 4 separate things, write them down, and then come back and combine 4 separate things. Oh my gosh. Let's do that then. 2 plus 1 is 3. 3 minus 13 is negative 10. Negative 10 plus 6 is negative 4. So if you had to evaluate something, which one would you prefer? The nested form or the direct form? Please say the nested form. Yeah, all things being equal, aside from the work of having to put it in the nested form is easier. Not only do you not have to memorize or remember values from term to term or write them down, but you don't have to exponentiate, right? I plugged in a 1 here. 1 cubed is pretty easy. But if I were to plug in like a 3 cubed is already getting kind of big. 4 cubed even bigger. 5 cubed even bigger. So you don't have to exponentiate when you use the nested form. It's just 2 operations, right? Multiply and add, multiply and add, multiply and add. So it's just a slightly different arrangement of factors that leads you to that. Now, is there a faster way to do nested form? Granted, it was a little bit of work to go from this first line here to this line here so that we were able to use nested form, right? Is there a faster way? And the answer is heck yeah, there is. And someone distilled the process. Here's a quicker way to do it. Notice all we're doing is we're multiplying by 2, and then we're adding 1, and then we're multiplying by 1, adding 1, multiplying by 1, adding 13, multiplying by 1, adding 6. So if you notice, the coefficients are the important thing. So a 2, a 1, a negative 13, and a 6. If you just write down the coefficients and you wanted to plug in a 1, here's how you would do it. Just put a little 1 in that box over there. Bring the 2 down, start it, and now this process, of course, we're familiar with. This is synthetic division / substitution. So notice the first operation we do after bringing down the 2 is we multiply. We got 1 times 2. Well, look what we did over here. The first thing we did was 1 times 2. And then we slid that up here into this column, and then the next thing we did was we added 2 plus 1. Well, that was the next thing we did over here, 2 plus 1. So we got a 3. Oops. And now once we had a 3, we multiplied by 1 again. That's what we're doing. And we slide it up there and we get a 3. And then we subtracted the 13. So if we add the column, it accomplishes the same thing. And now we multiply on the bottom, negative 1, or negative 10 times 1, which is what we did over there. Slide it up here. And then we added a 6, which is what we're doing. And we get negative 4. So there you go. The synthetic substitution, as we know it, as we saw it yesterday and you saw in Algebra 2, is basically the nested form simplified. You don't have to take all that extra effort of factoring out x's. You just write the coefficients out and do that little process. So it's much, much nicer. But direct substitution still has its value. Okay, it's still a good thing to be able to pull off because the caveat to synthetic substitution is that you do have to have a placeholder for anything that's missing. It has to be written in descending order, and you do have to have a placeholder for any x that's missing. And we'll talk about that here later on. All right, so if you were to plug in a 2 and a negative 3 and a 1/2, since it's the same function as we had up here, guess what you're going to get each time? You're going to get a 0. In fact, we did that already up here. They're all roots of that polynomial, so you're going to get a 0 when you plug in a 2, a 1/2, and a negative 3. Okay, and of course, when you plug in a 0, the function value being 0 means that it's a factor because that's also the remainder when you divide by x minus that number. Okay, so example 5 we could skip because we just kind of did example 5. Example 5 is basically doing the synthetic process, which I just showed you. I just did it in example 4. All right, let's look at this division algorithm here, which is kind of something we've already seen. It's basically the factor theorem, but it's stated a little bit differently. What is an algorithm, first of all? Is that a dance club owned by the disco dance club owned by the former vice president under Clinton? That's a long shot there. Yeah, no. Algorithm. What is an algorithm? You've heard it before, right? An algorithm. It sounds fancy, right? Sounds hard. No one knows what an algorithm is? Siri, what's an algorithm? I don't have Siri on my phone. How about it could be a pattern. Could be a pattern. A rule. I like that. It's a rule that follows a pattern. We can combine both of those. Yeah, that's what an algorithm is. It's a systematic procedure or systematic process that accomplishes a specific task. That's all an algorithm is. So here's the division algorithm. When you take a polynomial function f of x and you evaluate it at some value, call it a. Of course, we know that's equal to f of a, right? That is equivalent to dividing that function by x minus a. That's kind of the factor theorem, right? A little bit. If you know a root, you know a factor. If you know a factor, you know a root. Okay? But here's the important part. F of a, then, is not only the function value when you divide it by a, but it's also the remainder when the function is divided by x minus a. So we've seen it now when we have a factor, we know a root. When we know a root, we know a factor. But this is saying if x minus a is not a factor, that is, it doesn't go in evenly, and the remainder is not 0, then the function value is still meaningful. The function value still gives us something that's useful. It gives us the actual remainder. Okay, that's pretty cool. And of course, when the function value is 0, then we know that x minus a is truly a factor. Okay, that's important. So f of a is the remainder when you divide by x minus a. That's the general division algorithm. F of a is the remainder when you divide by x minus a. And of course, if the remainder is 0, then x minus a is a factor and x equals a is a root. Now, before I get to example 6, let me add a bonus example here, because I haven't amended these notes in quite a while, and here's what I would add. We'll call this bonus example, or extra example. How about this? What is the remainder when x to the 51st power plus x minus 3 is divided by the factor x plus 1? What is the remainder when the 51st degree polynomial is divided by the linear factor x plus 1? See if you can handle that on your own just for a little while, and then we'll see how y'all did. This is where you're trying it at home as well. You don't even need to hit pause. It's built right into the program. Makes a great test question right here, multiple choice. That's close, but not quite right. How'd you do it? You did direction of student. Perfect. I see all kinds of interesting methods unfolding here on these iPads. Some of y'all are going to need a little bit more time using the method you've chosen, right? Let's see. There are several ways you could do this problem. The whole thing is just screaming division, isn't it? What's the remainder when you divide something by something? So here's one way to do it. You can actually do x to the 51st plus x minus 3 divided by x plus 1. You can actually do the long division, right? And then at the bottom you'll have your remainder. We saw that yesterday and we're like, as much fun as that is, I think there is such thing as too much fun. And that might be it. That might qualify. Besides, why do conventional division when there is a synthetic method for doing so, right? So if we wrote down the coefficients, 1x to the 51st, 1x to the first minus 3, we could just synthetically divide with the root of x plus 1, which is negative 1. Now, there is a caveat to synthetic division, isn't there? Wow! We have to have a placeholder for every missing term that's not there. So, it would be 1x to the 51st, 0x to the 50th, 0, 49, 0 to the 48, 0, 0, 0, 0, 0, 0, 0, 0, 0, I lost count, 0, 0, crap, let me start over, 0, 0, 0, 0, 1, negative 3. Oh no, y'all want to do it that way? Does that seem reasonable? No, I don't want to do that. I could, but then I have to synthetically divide all the way down the line. And remember, when I get down here, that'll give me the remainder, right? That'll give me the remainder in this last box. But remember, this is also nothing more than the function value at negative 1. So synthetic substitution is nice sometimes, right? Nice sometimes. But direct substitution is also beneficial. And in this case, because we have so many missing terms, I think direct substitution is going to be a little bit nicer. So if I call that function f of x, f of negative 1 then is just going to be negative 1 to the 51st power is what? Negative 1. And then plug it in for x, you get minus 1, minus 3. There you go. You get negative 5. Aha. Direct substitution. Sometimes it's nice. Direct substitution, sometimes also it's nice. That's why it's nice to have two different versions. Yeah, so as it turns out, the remainder is negative 5. Therefore, is x plus 1 a factor of x to the 51st plus x minus 3? No, it is not, because it does not go in evenly. There you go. Nice multiple choice question on a test. And that is the division algorithm right there, right? That's correct, yes. Yeah, good. So, answering the question, thank you for keeping me honest. So the remainder is negative 5. Ergo, x plus 5 is not a factor. You can add that, but I didn't ask that. Okay? That's the remainder theorem. The function value at a is the remainder when you divide by x minus a. And now you have two ways to evaluate the function. Direct substitution or synthetic substitution. Okay, any questions on that? Fun, 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 or fun, 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 fun? Yeah, the second one. Very much so. Yeah, good. Especially on Hawaiian Day, right? Lay off drugs. Lay off drugs. That's the message of the day. Lay off drugs. Okay, let's do this. Example 6. Y'all got some time? Do we have time? We better do it together. We have about 5 minutes. If f of x is equal to a fourth degree polynomial, given that f of negative 3 equals 0, find all the zeros, and then write it as a product of the linear factors. Okay, so they're giving us this piece of information. What does it mean that f of negative 3 equals 0? What does that tell us about x equals negative 3? Good. X equals negative 3 is a root, and therefore x, what is a factor? X plus 3 is a factor. Good. So I already know one factor. I already know one root. Good. It is a fourth degree polynomial. And remember, our goal from yesterday is to get it down to a degree what at the very least? 2. If I can get it to a quadratic, then I'm home free essentially because I can factor it, solve it by separating the variables, or using the quadratic formula. So to get from a degree 4 down to a degree 2, I need to know at least how many factors? 2, right? And they only gave me 1, which means I got to find myself another. Okay, well, that shouldn't be too hard if you just think about it, because really all we're interested in is setting the whole thing equal to 0 and figuring out the 4 values of x possibly that work. Now, once you set something equal to 0, prior to this chapter, our goal was to what it? Factor it. And what's the first rule of factoring? Look for the greatest common factor. Do we have a common factor in all 4 terms? Why, yes we do. We have x. So it factors into x times something. Which means this is going to be a cubic polynomial. By the zero product property, I would say either x equals 0 or all that other stuff equals 0. So don't I know another root already? Yeah, I know 0 is a root. So that's why I'm just going to erase all that. If you just notice that x is a factor in everything, then you know that x equals 0 is also a root. And therefore, x is a factor. All right, so we basically have 2 roots. And what we're going to do to get down to the other 2 is synthetically divide them out. So here's what we do. We write the coefficients in descending order. 1x to the 4th, negative 13x squared, negative 3x cubed, and 15. Is that right? No, you can't just write the coefficients in the order they're given. You have to write them in descending order. So if you don't want to rewrite the terms in descending order, at least list the coefficients in descending order. So it's 1x to the 4th. Now I look for the cubic term, which is negative 3. And then the quadratic term is negative 13. The linear term is 15. And the constant is 0. Yes, you need a placeholder for everything, including if it's missing a constant at the end. Very good. Now I'm going to synthetically divide, and I should get a 0 in that last box. I get a choice now. Do you want to synthetically divide with negative 3 or 0 first? It doesn't matter. 0 is probably easier, so you could help yourself by doing that. All right, here we go. Bring down the 1, gravity. Multiply, you get 0. Add, you get negative 3. Multiply, you get 0. Add, you get negative 13. Multiply, you get 0. Add, you get 15. Multiply, you get 0. 0 plus 0 is 0. I knew it. So what we have now on the blue line, the depressed polynomial, is a third-degree polynomial. And because negative 3 has not been divided out, it's still a root of that third-degree polynomial. So this is how we chop it down to size. We continue the process on the depressed polynomial. So now I bring down the 1, and I try the negative 3, and I get negative 3. That gives me negative 6. That gives me 18. That gives me 5. That gives me negative 15. And boom, I end up with 0, like I anticipated. This now, depressed polynomial, is degree 2. So that's really 1x squared minus 6x plus 5. And now if I set that equal to 0, hopefully it factors. If not, I got the quadratic formula. X minus 5, x minus 1, yeah? Equals 0. So I know the final 2 roots are 5 and 1. So the 4 roots are, we're running out of time, the 4 roots are x equals 0, negative 3, 5, and 1. And the whole thing factors into x times x plus 3 times x minus 5 times x minus 1. And we're done. Okay? All right, we'll pick up there tomorrow with example 7. That's kind of the basic idea. Be chipping away at your homework. Blake, be out of here. Be long gone. If you need to leave before I'm done talking, I understand. It's not rude. Yeah. Anyway, be chipping away at the homework, and we'll try to finish tomorrow. The homework's going to be due on Monday regardless, so no big deal if we don't finish tomorrow. All right, have a good rest of the day.